Hi guys, I thought I would make a couple videos here on the two proportion notes, two proportion z intervals and two proportion z significance tests. These you can use for your reference and should help you finish up this unit and also for the next unit. The next two units actually. So here we are in the notes on two proportion z intervals. These have been posted on Google Classroom. And very similar to one proportion z intervals with a couple of minor exceptions. And that is, well, if we look at the background here, if we're constructing a confidence interval, we're essentially estimating the true population parameter or the true population proportion. With a two proportion z interval, we're looking at the difference between those two populations, and then we're going to estimate if that difference is significant. In other words, if 0 is contained in the interval, then that is a plausible difference between the two populations. In other words, there is no difference between the populations. Now, if we get an interval that's all positive, in other words, the low end of the interval is positive, the high end of the interval is positive, then we have pretty good evidence that there is a difference because the first population is greater than the second population in, well, if we use a 95% confidence interval, in 95% of the samples that we take, the first population, or the first sample from the population, is greater than the second sample, which means it's pretty likely that one population is greater than the other, or there's a significant difference between the two. Conversely, if the entire interval is negative or less than 0, the low end is negative, the high end is negative, then there's convincing evidence to whatever confidence level that you're testing here. The confidence level will determine the width of your margin of your interval based on your margin of error, right? If the entire interval is negative, that must mean that your second population is greater than your first population. So there is convincing evidence that there is a difference there. That's the basic gist. As with one proportion intervals, excuse me while I change my cursor here, we have to meet the requirements. Okay, and those requirements are no different except that we have to test both samples. And we have to determine that both samples are no greater than 10% of the population. And sometimes we have to make assumptions about the population because we're only given the sample size. And if you feel comfortable as a researcher making an assumption about the population, then you can check that requirement. And usually we do. Usually the population is pretty large. And the second requirement is that you have to have at least 10 successes and 10 failures, but this time for both samples. So you do have to check N1 times P1. P hat 1 is greater than 10 or equal. And N1 times Q1 hat is greater than 10. And since this is a binomial situation, we just have to look at the successes and failures. And there is a little typo here. There should be a hat over the second P2 right there. And of course, another requirement is that these are independent samples and they are randomly selected. Make sure that that is happening as well. Okay. Moving on to the point estimate. Okay, a point estimate is your best guess at the truth. And you get your best guess at the truth by taking a sample, or in this case, two samples. And we're estimating the difference between those two samples. So if we had both true population parameters and we subtracted one population from the other, we'd have the truth. Well, if we take two samples and we subtract those two samples or find the difference between those two samples, that is our best guess at the truth. So similar to the population parameter being equal to the sample statistic, the difference between the two population parameters we're going to say is equal to the difference between the two sample statistics, and that is stated there in symbols. Okay, generally, the margin of error for any confidence interval is the product of a critical value. Okay, that's your Z star. Critical value is the Z star that's associated with some confidence level, and the standard error. Okay, the critical value is based on the level of confidence, 1.96 for a confidence level of 95%. Remember, it's 1.645 for a confidence level of 90%. It's 2.575 for a confidence level of 99%. Those are your three common ones. Okay? And this would be one of the big differences with the two proportion Z interval, and that is that the standard error is calculated a little differently. So remember, you have to add, when you're finding a difference, a standard deviation difference, you still need to add. But that's really it. This left half of the formula is, and the right half, are just like one proportion standard errors. Okay, you're just going to calculate essentially the standard error for both samples. You're going to add them together and find the square root. And that is the standard error of the difference of two sample proportions. Okay, once you find that, you simply multiply that by your Z star, and that's your margin of error. And the difference between the two population proportions would fall between a low of the sample difference minus the standard error, the margin of error, and the sample difference plus the margin of error. And we would say that we are blank percent confident that the true difference between these two population proportions falls within the interval of blank to blank. Okay. And there is a note there that you don't have to memorize these formulas. You do have to know how they're constructed so that when you have your formula sheet, you know what you're looking for and you know how to use it. Okay, so let's do an example. This is the long way. Okay, the calculators give us some real shortcut methods, but you do have to know what you're putting into the calculator, and you have to know what the calculator is telling you if you are going to use that method. And you also have to justify your reasoning on exams, especially the AP exam. So here we have a random sample of 2,823 occupants not wearing seatbelts that were involved in car crashes, and 31 were killed. So not wearing seatbelts, 31 out of 2,823 involved in crashes, and 16 out of 7,765 that were wearing seatbelts and involved in crashes were killed. We're going to construct a 90% confidence interval for the difference in proportions of deaths, and that's no seatbelt minus seatbelt who were involved in car crashes. So we're estimating the truth. If it's no seatbelt minus seatbelt, and we're talking deaths, then hopefully we're going to get a positive difference here, right? Because the number of deaths for no seatbelt, we would think that proportion would be higher than those who were wearing a seatbelt, and I think we can see from those numbers already that that's going to be the case. So a two-proportion Z interval will be used because there are two random samples. It tells us that, selected from separate populations, and the difference in proportions of deaths in car crashes will be estimated. So you've hopefully seen from the AP videos that they remind you repeatedly to establish your parameters. Okay, so P sub 1, which is the population proportion for the first population, is the proportion of people not wearing seatbelts who die. And P sub 2 is the proportion of people wearing seatbelts who die, who were involved in car crashes. Check our requirements. We do have random samples from two separate populations. We must assume that people involved in crashes is 10 times greater than our two sample sizes. And I think it's safe to assume that. There's a lot of crashes in the United States each year. And finally, do we have at least 10 successes and 10 failures in both samples? And yes, we do. Requirements met. We're ready to move on. Point estimate would be the difference between sample 1 and sample 2. And that is going to be 0.00892. So there's a difference of about 0.9%, or 9 in 1,000. Okay, remember, sample 1 is those that were not wearing seatbelts, and sample 2 is those that were wearing seatbelts. The Z-star is 1.645 because we're calculating a 90% confidence interval. And then our margin of error, our standard error, is calculated here. I do want to point out there is a little algebraic manipulation going on in this formula. You'll notice that the denominators are cubed. That's not something that you need to know how to do if you want to convert those fractions, those proportions to decimals, and then subtract them from 1, and then multiply them in the numerator and divide by the sample size. As the formula says, you're welcome to do that, but I will show you quickly why those denominators are being cubed. If we leave our proportions in fractional form, and I take 31 divided by 2823, which is P1 hat, and I multiply that by 2792 over 2823, which is Q1 hat, or 1 minus P1 hat, and I divide that by the sample size, N1, 2823. If I algebraically change this a little bit by, instead of dividing by 2823, I multiply by 1 over 2823, I end up with, I'm just going to move this up to the top, 1 over 2823, which gives us the following. And you can see that is 31 times 2792 over 2823 times itself 3 times in the denominator. Sorry, that's not coming out very well, but that's why that's written there. Okay, it really would be the best way to do it because there's no rounding happening. If you convert your proportions to decimals, you are going to have to round, but that's fine. Just make sure that you include enough digits after the decimal if you are going to convert those to decimals right off the bat. Okay, so moving on. We calculate our standard error. We multiply that by our Z-star, and we end up with a margin of error of 0.00334. Okay, so give or take, right? Give or take the difference in our sample proportions, this margin of error of 0.00334, you can see that being subtracted from our sample difference and added to our sample difference. In the middle, we're saying the truth lies 95% of the time. We end up with this confidence interval at 90%. So I was about to say how to interpret that, because that is my knee-jerk reaction, and it should be yours too. You got to interpret that confidence interval, but here it is. One way to say it is we are 90% confident that the difference in the true proportions of deaths, not wearing seatbelt minus wearing seatbelt, is between those two numbers. Now, notice that the entire interval is positive. 0 is not contained in that interval. That is convincing evidence that there is a significant difference between these two populations. And since it's positive, there's convincing evidence that the first population, which is those not wearing a seatbelt and dying, is greater than the second population, which is those that do wear a seatbelt, that did wear a seatbelt and died. Okay, hopefully that helps. That's the gist for building a confidence interval for the difference of two populations, or a two-proportion Z interval. Next video, I'll show you how to do it very simply with the calculator.